Hello, my name is Dmitry Glukhov, and I represent a research of genetic algorithms to search for an analytical model of the relationship between input and output variables in data. This research focuses on the method of identifying analytical dependence in conditions where the model is unknown. If we know the model, then we can use regression analysis and other mathematical methods to identify the parameters of the model. However, if the model is unknown, if there is a situation of indetermination regarding the form of dependencies, then we are trying to build empirical dependencies from our intuition. This works well in simple cases of two-dimensional dependencies. But in the case when we have a multidimensional space, our imagination and intuition are ineffective. We have experience build a multi-agent system using local heuristics to solve model identification problem. However, local heuristics are good for one specific case and are not universal. Therefore, we attempt to build a universal tool for determining the multidimensional analytical model that describes the relationship between empirical data. A genetic algorithm is also a heuristic search algorithm used to solve optimization and simulation problem by sequentially selecting, combining and varying the desired parameters using mechanism that resemble biological evolution. Previously, we made attempts to solve this problem on multi-agent systems, which for analytical models in the three-dimensional space of variables showed results superior to results of artificial neural network, but on a limited variety of models. The main disadvantage of such approximator is a limited set of structure transformations formulated in the forms of local heuristics. Heuristics are obvious ways for a human expert to change the structure. Accordingly, modifications that are not obvious to the expert become impossible. In our opinion, the use of genetic algorithm removes this restriction. In addition, we have built approximators based on fuzzy logic. If we consider the unknown parameter as continuous, then in this case we can make a parallel between the conclusion about the value of the unknown parameter and the approximation of the function, and talk about the property of fuzzy system to act as a linguistic approximator. The advantage of such approximator is their speed, and the main disadvantage the limited opportunities to improve approximation accuracy. To implement the genetic algorithm, we propose as a genome a parser tree of the LR1 parser of a context-free grammar. The context-free grammar of the analytical model used by us is presented on the slide. In the process of syntactic parsing, as we can see, the right side parsing tree is built in the form of an object-oriented structure. In order to be able to compile an algebraic expression into a tree of objects nested into each other, we have developed a class system presented in the class diagram. As a result of syntactic parsing, the initialization file, an initial population of analytical n-dimensional models, is created. Initial variations of the models are formulated by an expert in the formal language of the grammar. As shown in the slide, the genetic algorithm is a sequence of specific transformations of a population. First of all, initialization of the population with expert-defined algebraic expressions for the case of n-dimensional variable space. Second, calculating of the approximation error for each individual in its current state. Third, the process of random cloning with a coefficient mutation in order to avoid a local extremum. Next, the process of cloning with a structure mutation, subject to positive effect of the mutation. Next, the process of searching for the extremum of the target function in the coefficient space. In the implementation of this process, we have chosen the gradient descent algorithm, but using coordinate relaxation. This algorithm is not fast, but it is reliable enough. And the last stage, it is a simplification of the structure of an expression in specific cases. As the objective function, we have chosen the standard deviation between the theoretical and calculated values of the function. In the m-dimensional space of coefficients of analytical models, the standard deviation surface may have local extremes due to the limited data area and the complexity of approximated dependencies. However, the character of surface allows us to suggest the possibility of using the gradient descent algorithm to search for a local or global extremum. The character of the standard deviation surface in the space of two coefficients a and b of a function of one variable is illustrated on this slide. Given that we are trying to minimize the standard error of the deviation of some analytical function from a discrete data set, we conducted a comparative analysis of the applicability of various numerical optimization methods and provide the user of the system with the choice of a specific method. Our approach is based on 2 points. First of all, the mutation of coefficients is necessary for an abrupt transition to a new extremum search point, which allows the algorithm to run several extremum search strategies from different areas of the n-dimensional search space, and therefore to avoid getting into local extremum. And the second, application of the most qualitative method for finding the extremum depending on the specific of the problem. In our numerical experiments, the best convergence rate was shown by the coordinate descent method, in which the step is performed along the coordinate giving the maximum gain. However, the search and implementation of more efficient optimization algorithms remains the subject of further research. It is important to know that we have proposed a new method for screening out equivalent formulas. This method is based on calculation on some specific hash. An example of the operation of this hash function is shown on the slide. As an example of the application of the genetic algorithm we constructed for solving an applied problem, we consider the problem of accounting for transients in stationary non-isothermal model of gas transportation. Formulation of the problem. When the compressor station is switched on, gas heating begins, and despite the fact that the heated gas has not yet spread through the pipeline, the stationary model describes the state of the pipeline that will occur after the transition to steady state. Thus, significant sections of the pipeline in the model are found to have an overvalued gas temperature, and given the strong dependencies of gas density on temperature, with an underestimated value of the gas reserve, we calculated the correlation coefficient, which for the considered areas with temperature increase showed a high negative correlation. So for the four graphs given, for example, on slide, the correlation coefficients are presented. The solution found by a genetic algorithm exceeded in accuracy the fuzzy logical approximator with selected optimal smoothing settings, while giving the most compact representation of the approximator. The dynamics of improving the approximation quality can be demonstrated by the graph of positive mutation. This graph presented on the slide. One of the parameters of the proposed genetic algorithm is the limit size of the formula, which allows to obtain a wide variety of compact variants of approximator. The developed genetic algorithm has the possibility of flexible adjustment of limit thresholds of population size, percentage and death period of unpromising individuals, the probability of a period and type of mutations of the structure and coefficients, formulations of model simplification tools, algorithm of search of extremum. So, we can draw the following conclusions. First, search space encoding is performed as a parsing tree of an algebraic expression by the parser of the context-free grammar of the class LR1. Second, in the course of the evolutionary process, in addition to the use of structure mutations, provided their positive effect, the stage of coefficients mutation is performed, which allows avoiding the target function falling into local extremes. Third, at each step of the evolutionary process, there is a stage of searching for an extremum in the coefficient space and the stage of simplifying the analytical model. Thank you for your attention.